Okay, everybody, on this question we're trying to find out which of the following is the strongest base. Now remember the reciprocal relationship between acids and bases. The stronger the acid, the weaker the conjugate base. So, if we consider the respective conjugate acids of all of these, when we're assessing base strength, we can always think about their conjugate acids. So which one of these is not like the other? We have here 4 strong acids and 1 weak acid. Which ones are strong? Well, HCl is strong. H2SO4 is strong. HCl3 is strong. I'm really just crossing these out in an arbitrary order. HBr is strong, which means that all their conjugates are negligible. The only base here that we can consider a weak base and not a negligible base is ClO2- chlorite ion. Okay, for this problem we can take 2 approaches. We can either use our thermodynamics equations that are marked here to think about this, but probably a simpler way is to consider Le Chatelier's principle. So let's look at reaction A first. So we can see here what happens as temperature increases. So the first reaction was done at 500 Kelvin. The KEQ was 178. Then, when the reaction was performed at 700 Kelvin, a higher temperature, we can see the KEQ got smaller. So that means as temperature goes up, the reaction is shifting to the left. So I have here some arbitrary reaction. A goes to C. If the reaction shifts to the left at higher temperatures as we add more heat, that means that we can consider heat to be a product. Okay, if heat is considered a product, that means we're looking at an exothermic reaction. So this first one here is exo. Let's take a similar approach for evaluating reaction B. So if reaction B is some reactant B turns into some product D, what do we have going on here with regards to temperature and the equilibrium constant? So at 300 Kelvin, the KEQ is 150. At 600 Kelvin, it's 195, which means as the heat goes up, the products become more favored. So we can consider heat to be a reactant. Again, a way that we can think about this in terms of Le Chatelier's principle is as we increase the amount of reactants, in this case heat, the reaction would shift to the right. So this is an endothermic reaction. So that means that the one that correctly describes what we're looking at is B. Reaction A is exothermic, reaction B is endothermic. Up next, we're evaluating absolute entropy. So here are, here's kind of the laundry list of things that we look at when we evaluate what molecules have the most entropy. Since we're looking at the highest gas phase entropy at 25 degrees Celsius, that means the temperature and the phase are both the same. So we're just using these 2 criteria. So the first thing we look at is how complex is the molecule. The more atoms that are bonded together, generally speaking, the greatest absolute entropy there is. Then after that, if there is a tie, we'll look at mass. But if we look at the possible answers here, there is one that stands out as by far the most exceptionally high entropy, and that is choice D. This is propane. It has a total of 11 atoms, which is more than any of the other choices. Okay, here we have another Le Chatelier's principle problem. So what are we going to do? Well, let's take a look at how changing each of these concentrations will affect our equilibrium. Okay, so the first one says decreasing the volume of the reaction vessel. To consider this, what we need to do is we need to consider that there are 2 moles of gas in the reactants and 3 moles of gas in the products. So if we decrease the volume of the reaction vessel, what happens to pressure? Well, that means that pressure in general would go up. Le Chatelier's principle says that the reaction will shift then toward the side of the reaction that corresponds to less pressure to help alleviate that. So which way would that be? Well, it would shift to the left, because that would help, since there's 2 moles of gas in the reactants and 3 moles of gas in the products, shifting to the left would help alleviate some of the pressure. So this is not going to increase our amount of nitric oxide. The next one says decrease the partial pressure of NOCl. Let's consider what that will do. By decreasing the partial pressure, and therefore the concentration of a reactant, the reaction will then shift to the left. Once again, this would decrease the amount of NO because we'd be shifting away from the product. So this isn't going to get us the job done either. Increase the total pressure by adding N2. Will N2 do anything to change our concentration of things if it's not involved at all in the reaction? Dun 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 dun. No. No, it will not. Increasing the volume of the reaction vessel. Now this is kind of the opposite of choice A, and considering it's the opposite, what will it do? Well, if we increase the volume, that means that the pressure of this entire system would drop, and if the pressure of everything's dropping, this reaction's going to shift to the right to make more products, which means we will indeed get an increase in NO. So choice D, FTW. Okay, now one of these infamous problems. For which of the following reactions below does delta G standard of the reaction equal the delta G standard of formation, specifically of the product? Basically, there's just two things we have to look for here. First, we have to make only 1 mole of product, and then the second thing is all the reactants need to be in their standard elemental state. So we can actually eliminate a number of these answers right off the bat. So for example, here we're making 2 moles of product, nope. Here we're making 3 moles of product, nope. Down here we're making 3 moles of different products, nope. So left with choice C and choice D. And then the one that's going to win here is the one where the reactants are in their standard elemental state. So it's going to be choice C. All reactants are standard elemental state. We're only making 1 mole of product. And when you think about it, if we plug into the delta G standard of the reaction equals products minus reactants rule, what will we get here? Well, we would get the delta G standard of the reaction is equal to the delta G standard of formation of the products, which is 1 mole of the N2O4, minus the delta G standard of the reactants, which for N2 gas and O2 gas would be 0 plus 2 times 0. Basically, this is all 0. This whole thing cancels out. And we get this relationship that we're looking for here. Neat.